Now, let's look at some specific examples. If we look at the reaction of toluene. Now, the reaction we're going to take in general here is comparing the exact distributions for nitration of the substituents that we're looking at. So with this, of course, there is an ortho, a meta, and a para product that can be formed. What do you think? Which is going to be major? Is it only going to be one of them? Is it some of all of them? Mostly one? Okay, let's look at the distribution pattern. So the experimental distribution pattern for this is 63 to 3 to 34. Okay, remember we have an ortho, a meta, and a para substitution product. You should go take as an exercise, draw the actual product of the ortho, the meta, and the para here. Here's the general pattern. You draw the specific one. Okay, this is one of the big stumbling blocks for students of organic chemistry. They can't translate the general to the specific. So you go draw these. I'm giving you the ratios of them. So what we see here is that when we have a methyl group, which is illustrative for alkyl groups in general, that we get very little of the meta, and we get mostly ortho and para. Okay. Now let's look at a slightly different compound. What if we have a fluorine? Under, again, the same conditions, and so the two single quotes or squotes means bring down the reaction conditions from above. That's nice shorthand when you're taking notes on things. And what we see for this is 13 to 1 to 86. Can't do my math this morning. 13 to 1 to 86. Now, again we see there's very little meta and mostly ortho and para, although the major here is para, whereas the major was ortho before. Now, fluorine and methyl are illustrative of what we call ortho-para directors. Okay? That is, the substitution pattern predominantly forms ortho and para products. Ortho and para, para and ortho. So these are illustrative of our class of ortho-para directors. Now, the alkyl group I chose here specifically. So this is the alkyl groups are the only ortho-para directors that don't have lone pairs. What you'll see is that for the ortho-para directors, almost all of them, again with this exception, will have lone pairs on the atom adjacent to the ring. That is, the atom bonded to the ring. All right, well, let's look at something. Now, again, these are typically electron donating groups. Okay? Not formally, but you can see how electrons get donated to the ring. We'll illustrate that in a few minutes. Okay. Now, the other class is where the aromatic substituent is withdrawing electron density from the ring. Alright, so what do we want to take as our first example here? How about the nitro group? So if we consider the structure of the nitro group, you have a nitrogen with a plus charge next to the ring. Of course, there's a negative charge to balance that, so it is neutral. But as you can imagine from simple Coulombic inferences, that the positive charge is going to withdraw electron density. And in fact, I'm going to go ahead and illustrate it for you here with resonance. If we look at this resonance form, that resonance form has removed electron density from the ring. Let me get the rest of my formal charges in there. By resonance, this resonance form has put a positive charge at that ortho position. Okay? So that's removed electron density from the ring, and as I mentioned, electron withdrawing groups are going to make the reactions go slower. Now, let's look at the distribution of products for this one. For this one, we get 791 to 2. So for a nitro group, when we make what will become the dinitro compounds, we get 7% ortho, 91% substitution at the meta, and 2% substitution at the para position. So overwhelmingly now, this is what we would call a meta director. It's a meta director because the meta is the major product. And of course, what we would see with these is that the polarization of the molecule, these have very different polarities, and we would be able to separate those fairly reasonably and fairly easily, either by distillation or by chromatography. So sometimes they will have very different boiling points, because of course the para substitution down here, you can imagine the two nitro groups balance each other out, and the para would be very nonpolar. Ortho substitution would be the most polar, and then the meta substitution would be intermediate in polarity, and so boiling points would be different. Melting points might be different also, so you can do fractional crystallization, or you can do fractional distillation of these, or as a last resort, you can do chromatography to separate them, because they would typically separate on chromatography. All right, so there's the nitro group, and then finally one more. A carbonyl group. This is acetophenone, this compound where we have a methyl group here. And again, under the conditions, and again, we're bringing down these nitration conditions. The distribution here is 26, 72 to 2. So there's a little more ortho nitro acetophenone than para acetophenone, but clearly the majority of the product here comes with meta substitution, right? That's 72, 26 to 2. And again, I want you to take these as exercise. Go for all of these. Draw all three products, the ortho, the meta, and the para substitution products for these. So carbonyl groups are also electron withdrawing groups. They reduce electron density from the ring, and they are in our class of meta directors. Now, I need to go back and make sure I clarify. The methyl group is electron donating. Fluorine, by inductive effect, is actually an electron withdrawing group, and it's a unique class of electron withdrawing groups, so the rate is slower than benzene, but the directing group effect is like an electron donor in that we get ortho-para preference for products for the halogens. And we'll talk more about those shortly.